the Tectonic seminar series. So this is a more, let's say, well hashed out version of the talk. And like I said earlier, if you have any questions, just feel free to interrupt me. I can't really see anyone at the moment, but I'll pull you up if I hear you asking me any questions. So yeah, I'll be talking a little bit about some of the work that I did during my PhD to try and look at some precursor slip and asperity deformation in experimental faults using ultrasonic monitoring. This work builds up on a lot of cool stuff that Brian Kaproff and also Marco Scuderi did on the Penn State apparatus and also in Rome over the past few years. So really cool stuff that it builds up on. And before I dive into the science, I just want to take a moment to quickly shout out to some of the folks that have helped me with this process along the way. Chris, of course, Jacques and Parisa in the Penn State Ultrasonics Lab. And some of you may know Chaz, who was a colleague from the same cohort at Penn State with me. And he's also helped me a lot with some of the machine learning aspects, the prediction work that I'll be talking about later on in this talk. And of course, all the funding agencies who have supported my salary and equipment and supplies. Okay, so as I begin, I just want to sort of iterate that earthquakes are pretty complex frictional instabilities. And I'm sure I don't have to stress on that to this group here, but of course that has to be said. And over the past decade or two, we've documented a variety of slip modes in nature, spanning tremors, VLFEs, LFEs, and slow slip events in the seismic as well as geodetic signatures of frictional instabilities in nature. And these have been used to bridge the gap between aseismic creep and dynamic ruptures. And infrequently, we also have some interesting pre-seismic phenomena that record some information about what we think may be impending seismic events. And I'll give you a few examples of that from nature in the next few slides. So I am exploring the earthquake precursor and forecasting problem for slow and fast lab earthquakes. So when I'm talking about precursors, I'm thinking about any pre-seismic process that could contain some information about the timing and or size of an eventual seismic event, be it slow or fast. And I'll talk about that a little bit later on. So in particular, we've had a lot of recent uptick in interest motivated by some field and lab observations of what we believe may be anomalous pre-seismic signatures. So for example, in nature, I don't know if you can see my cursor maybe, Fenglin New and others in this example here performed a very high temporal resolution cross-borehole active seismic experiment on SAFOD and reported a pre-seismic velocity reduction of almost almost half a day prior to a tiny magnitude 3 event in 2005. Now in the lab, we've routinely documented some really robust pre-seismic velocity reductions. This is what I'm talking about from Brian and Marco, of almost 2 to 3% before both slow and fast earthquakes or lab quakes. So even though we've documented robust signals that we think are precursors, we don't yet have a particularly great handle on the physical mechanisms that are responsible for these anomalies, specifically the amplitude and the velocity, the p-wave amplitude and the p-wave velocity signatures of these precursory anomalies. So this is a notable example, like I just said, of the magnitude 3 earthquake in the San Andreas fault, which goes off right here by this black line. So the cross-borehole seismic recorder, which is a control source, so what that means is that you're pinging and recording across a fault multiple times throughout the day. And what they document is a travel time delay, which can be translated into a velocity, assuming an effective continuum. And these waves of velocities are reducing by about 2 or 3% for almost half a day before the event. And it continues to decrease post-seismically here. Another example, this is super interesting to me, is before the magnitude 8.1 Iquique main shock in 2014. So during an 8-month lead up to the main shock, we observed a lot of precursory slow creep followed by some intense foreshock activity that eventually culminated in the magnitude 8.1 main shock event. So there was a lot of precursory slow slip and triggering that preceded the main event. Now, switching gears a little bit, I just want to demonstrate that this kind of phenomena is not only isolated to earthquakes, and it can also happen in other granular sliding phenomena, for example, like in this landslide here. So what I'm showing you is an example of a landslide in Greenland, and for about 10 hours prior to the main event, again, a red line right here in time, local seismic stations captured some tiny seismic events that build up in numbers and size. So potentially, if there was more instrumentation and if we knew where to look, that's sort of the crux of the problem, there could have been some predictive campaign using, say, inverse velocity or something like that. So the issue with all of these examples is that often we only realize the existence of these precursors after the main event has occurred, partly because we don't really know where to look or what's going on below our feet. And that's sort of what I'm trying to chip away at in this talk here. Okay, so now that we sort of recognize the problem, I just want to restate my goal for the talk. And ultimately, it is to understand failure in geologic media at sort of the hundreds of meters to kilometer scale, such as this beautiful example of this fault here. And conventionally, we've done this by conducting friction and mechanical experiments on rocks and faults at the centimeter scale, which is sort of the laboratory rock friction and deformation experiments. But fundamentally, the friction for both of these cases originates in sort of the microscopic load-bearing asperities that make up a fault zone. And these are just typically a few microns or a few nanometers wide. So I want to try and gain insights into the frictional and deformation mechanics of these systems using constraints from both these friction experiments, sort of the conventional friction experiments, as well as ultrasonic monitoring, which taps into this parameter space on the micron scale here. So in this talk, again, even though I showed you examples of a landslide, I'm just going to specifically address earthquake as a failure event. Okay, so then at this point, perhaps the natural question is, what can the ultrasonics tell us that conventional friction experiments cannot? And this sort of takes me back to this really cool figure from Dietrich and Kilgore in 1994, where they used a similar theory to show how light intensity can be used to probe elastic contacts. And we sort of adopt the same mechanism here. And the idea is that the sort of high frequency ultrasonic waves that we're using in the study have wavelengths that are longer than the width of these faults right here. So when the pulses propagate through the rough faults with these tiny load-bearing asperities or contact junctions, they can either pass through an asperity, which is stuck, like this example right here, and then, or they can pass through a gap, like on the left here. So when the pulses pass through an asperity, there's less transmission losses, and as a consequence, the amplitudes that are transmitting through and the velocities tend to be higher. If they pass through a gap like this on the left, then the waves are disrupted, and so the amplitudes and the velocities will tend to be smaller. So by looking at the size of these amplitude and velocity signatures, we can say something about the strength or the stiffness of these asperities. Specifically, these properties of the pulses can be connected to the contact normal stiffness and the real area of contact of these asperities. And hopefully then it can tell us something about the precursory slip that we observe in our experiments. So if you're interested in learning more about this stuff specifically, some work that we did in 2019 or published in 2019 sort of goes deeper into how we connect the ultrasonic properties to the contact area and contact stiffness. I'm not going to be discussing that in much greater detail here. And this sort of brings me to one of the main points of the talk, is what are the physical or the sort of frictional or grain scale origins of these precursors, and how can we leverage them for forecasting. The experimental methods are sort of similar for the entire talk, so I'm just going to spend some time talking about it. So what we do is perform experiments on a pretty standard sort of double direct shear configuration in the biax at Penn State. And for those of you that may not know what this is a pretty huge hydraulic press with two axes. A horizontal axis provides normal stress in this double direct shear 3-block configuration, and the vertical piston provides the shear stress or a constant background shear loading rate or strain rate on the longer central forcing block. So when you move this block down, you're shearing these two faults, and the contact area, the nominal frictional contact area, remains the same throughout the experiment. So the sort of difference where this experiment protocol deviates from sort of the conventional experiments that we're used to in sort of the friction community maybe is that we use a very fine layer of quartz gouge between the granite blocks. And so when I say fine layer, I mean it's literally 150 to 200 microns thick. I do this by weight, so it's tiny amount of quartz gouge between the granite blocks, and the role or the purpose is to simulate some wear and fault maturity. So instead of this, potentially, I could just run maybe 100 or 200 full cycle experiments to collect enough gouge, but instead I just sort of artificially speed up the process by introducing a fine layer of quartz gouge here. And we found that adding this increases the complexity of the system, and I'll just tell you what I mean in just a second, and helps us produce intermittent, slow, and fast slip events. So in these experiments, we sort of modulate the event size and duration using acrylic springs of very different cross-sectional areas in series with the shear loading piston. So a thicker acrylic spring makes the system stiffer, and so we get slower slip events or aseismic creep. As you go thinner, your stiffness is reduced and goes far below the critical sliding stiffness K sub C, which means that you get faster and faster events. So we're able to modulate the lab earthquake size at the same normal stress and strain rate. Okay, so the reason we do this instead of modifying the normal stress and strain rate is that we want to keep the sort of starting real area of contact the same, and changing the normal stress or the strain rate means that the aspirity contact area would be different from experiment to experiment, and we did not want that. Okay, so the other thing that I do, which comes from the title of my talk, is we're measuring ultrasonics. And this is measured by pulsing from one side to the other side constantly. So in this experiment, or in these experiments, we pulse about 1,000 times a second. And we record the pulse at the other side and use specifically the peak-to-peak amplitude and the first arrival of this yellow wavelet here for all of our analyses. Presumably, we could use the coda waves as well, like what folks have done in the past, like Elisa, for example, in her JGR manuscript. But the reason we didn't do that was just that we could see very clear variations and signatures in the first arrival itself, that we didn't feel the need to go to the coda to be able to look at clear precursory variations. Okay, so in this slide, I just want to provide a brief overview of what the experimental results look like and what I mean by the complexity that I was talking about in the previous slide. So on the right, I'm showing you a sort of typical experiment with friction measured as the ratio of the shear to the normal stress on the y-axis and the far field displacement on the x-axis. This black band here contains hundreds of lab seismic events, which again is pretty cool and interesting for these forecasting and precursor problem, because this is a parameter space that you cannot tap into in the Earth, where you just go and collect hundreds of events from the same source. The inset shows a few of these lapstick slip events. And you can see here they have a range of stress drops and event sizes and reoccurrence intervals in just a tiny section. And this is what I mean. Like, without adding the quartz gouge to the fault, you don't get this rich range of seemingly random behaviors. And this is particularly useful when I talk about the prediction studies later on in the talk. Okay, so now in the next slide, I'm going to show you a couple of end member lab quakes more carefully. And by end member, I mean really slow and really fast. Okay, so the top panel shows a fast dynamic event, which would, you'd hear a bang in the lab during the co-seismic phase. And this bottom panel shows a really small slow slip event. So the long shear stress or friction increase here is the interseismic strain accumulation period. And this drop is the stress drop, the co-seismic rupture, where the fault is slipping once the spring cannot stretch anymore, for instance. The slow event, you can immediately see, has a much longer co-seismic slip duration and a much smaller stress drop. So next on this plot, I'm overlaying the ultrasonic amplitudes, or I call it transmissivity in these slides, on top of these plots. So you make a couple of interesting observations. First, it seems like the amplitude has very robust pre-seismic reductions in the amplitude for a long period before the eventual fault failure. And it seems like the size of this, so the size of A max to A co-seismic, seems to be higher if the eventual stress drop is higher. And like I said, it also starts to reduce far earlier for larger events as compared to the smaller events relative to the size of the entire earthquake reoccurrence interval. So next, I plot the fault slip rate on a log scale. And a really remarkable observation is that there's a strong correlation between the slip rate and this transmitted amplitude that we observe. And it seems like the amplitudes are very sensitive to small amounts of pre-seismic creep. And I say this because the slip rate is on a log scale. The relationship between amplitude and slip rate is a logarithmic one. So even a small pre-seismic creep signature could potentially show a large amplitude reduction signature as long as there's enough sort of acceleration associated with this creep. And so the idea is that the fault experiences a reduction in the microscopic contact area as it starts to creep interseismically. And
sorry, Srisharan.
Yeah.
Here you are testing the same fault.
Yep.
And the difference from slow to fast is induced by the stiffness ratio?
Yes.
Okay, thank you.
Yeah, that's correct. Thank you.
And sorry, another question on this regard. And the slip velocity function that you plotted there, it is what you measure from the machine, it's not imposed.
Yes, so this is not the far field strain rate that we're imposing. This is what you get at the fault itself. Maybe I can actually, yeah, that's a really good point. So we measure that by straddling a slip sensor very close to the fault. So this one is only measuring the slip rate of the fault. And this sensor here is what drives the background strain rate. So they're two different things.
Can I see again the previous picture?
Sure. Oops, sorry. You mean this one here?
Yeah, so
okay.
This means that you call fast because the gradient of the slip acceleration is fastest for the top panel with respect to the lower one, no?
Right. So you could also think of it as a ratio of the peak slip rate to the driving rate. So in this case, the ratio, so our driving rate is about 10 microns per second. So in this case, the ratio is about 10 because the peak slip rate is 100. In this case, the peak slip rate is more like 3 millimeters or 4 millimeters per second. So the ratio is much higher.
Yeah, and these results does not depend on the stiffness ratio, because you have the same correlation almost for both.
Well, I'm not sure I follow, because the stiffness ratio should be different for the different experiments by design.
Yeah, but you see that in both cases, the two panels, you see the same correlation between the logarithm of slip rate and the amplitudes.
Right. Yeah, that is
both.
independent
So
of. Sorry, go ahead.
No. Sorry, for both you see the same correlation.
Yeah. So that's a very good point. That correlation seems to be inherent to the aspiratory deformation itself, and that doesn't seem to have anything to do with the sort of background conditions. Or yeah.
Yeah. Thanks.
Yeah. Thank you. Okay. So that's a really good point, and that's sort of the main takeaway, is that this amplitude versus log slip rate relationship is very robust and remains regardless of what background conditions you have. And I want to mention here that this relationship persists even during stable sliding. So for example, if we conduct multiple experiments where we're just aseismically creeping at different slip rates, the amplitude still follows a inverse log linear relationship with the slip rate. And that result has been reported in that the 2019 JJR manuscript that we showed you earlier. Okay. So then I guess one question that we could get at is sort of the question of the precursor timing and its relationship to the eventual lab earthquake size. Maybe think about extrapolating or extending this to natural systems, and what might that mean for that. So I'm showing you here the stress drop, static stress drop, which for the lab earthquakes is a measure of the event magnitude, in this case, because the entire fault ruptures. So the stress drop can be thought of as your MW, for example. And the duration of these amplitude precursors here as a function of the pre-seismic creep, which is again measured from the slip sensor. And this is for a number of events for different springs, so different boundary conditions, different K over K sub C ratios. And you observe an interesting relationship. It seems like the larger events are associated with a longer precursory signal. So the larger events is this band right here. They have a much longer precursory signal, the precursor duration, even though they have almost no pre-seismic creep in an absolute sense. Whereas the smaller events, which is this rectangle here, have much smaller precursory signals and smaller stress drops, even though they have a lot of precursory creep. And this is because the fast events have a very tiny or a very slow precursory phase that lasts for a very long time. So the total creep is sort of distributed over a larger amount of time. Whereas for the smaller events, you experience a precursory signature for a shorter duration. And again, this sort of goes back to the inverse log linear relationship. And so as a consequence, the larger events end up having a very long-term precursor, even with a tiny amount of precursory slip in our experiments. So that was sort of all about the amplitudes, which sort of still leaves us with the ultrasonic velocities that even folks before me have very robustly recorded as having precursory signatures. So going back to sort of a snapshot of multiple seismic cycles from our experiments on the right, you can immediately see that for a given seismic cycle, so here they're all very similar to each other, very periodic, very constant reoccurrence interval. Even for any given seismic cycle, let's take the middle one right here. You have the co-seismic rupture right here. The amplitude precursor seems to onset very early during the intraseismic, which I showed you in some of the previous slides as well. Whereas the interesting thing is that the velocity anomaly seems to only onset very close to failure. So just a little bit before failure. So physically, if we assume, based on the sort of model that I showed you earlier, that the amplitudes and velocities are linked to contact deformation, this doesn't make any sense because they should be tracking the same quantity and moving very similarly. Even though these changes are tiny, they are consequential, as I'll show you later on. So to better understand what's going on, we sort of started to think about partitioning the effect of the wall rock and the fault zone on the ultrasonic wave signatures. So we did this by using some of Jacques and Parisa's expertise in what is called dynamic acoustoelastic testing. So what we do for this is we run a series of calibration experiments, which is these ones on the right. And we take a block of granite in these calibration experiments of the same length and cross-sectional area as the double direct shear experiment set up on the left, which is the normal sort of conventional friction experiments. And then we subject this block to the same horizontal and vertical loads as the friction experiment. And because the vertical load here is not strictly speaking a shear load, it's just some actual load. If you need to do something funky to sort of, simulate the stress changes during stick slips. And we do that by oscillating the vertical load over a range of frequencies and amplitudes that are consistent with the interseismic duration and the stress drop of the stick slip events in this case. So this type of testing is known as dynamic acoustoelastic testing, and the nonlinear acoustics and non-destructive testing community, particularly popularized by Jacques and Parisa, tend to use this a lot. And it's typically used to quantify the nonlinear elastic response of a homogeneous medium. So it seems like it's used more commonly in steel and other metals, but we sort of took a version of it to use in our experiments to get at the nonlinear response of the wall rock itself. So this is sort of a quick and dirty walkthrough of the results of this testing on the intact rock. So this is what I mean by different amplitudes and frequencies that we're oscillating the vertical stress at. So this captures the elastic wave response at frequencies that are consistent with the interseismic here, so very low frequencies, to 1 Hertz frequencies, which are more consistent with sort of the co-seismic duration of the more dynamic events that we see in our experiments. The blue curves are the P-wave velocity response, and the red curves are the P-wave amplitude response, or the yellow curves. Red is just a moving average, which reduces some of the noise from that. So to a first order, what we immediately noticed was that the pulse velocities are far more sensitive than the amplitudes to stress variations in the wall rock. So you can see that the amplitude does react a little bit to the peaks and troughs of the stress, but overall in a percent sense, it's nothing. Whereas the velocity is a substantial percentage of the base velocity in comparison. So from this data, you can sort of calculate a stress versus velocity and stress versus amplitude relationship. That's what I'm showing you here in a sort of piecewise linear fashion or assumption. And the slope of that calibration, the stress versus velocity or stress versus amplitude, will tell us what the nonlinear response of this wall rock is. And using that, we can remove the nonlinear response of the wall rock from our mechanical results in the stick slip experiments, which is what I'm showing you in this slide here. So on the left, we start again with the shear stress response for a single event in the experiment. And I'm going to bifurcate this response into an interseismic, which is a fully locked period where the stressing rate is equal to the stiffness, a pre-seismic period, where the stressing rate is lower than the stiffness, so which means that this is the onset of sort of pre-seismic creep in our experiments, and finally a co-seismic rupture, which is simply where the stress starts to reduce. Okay, so when we look at the transmissivity response for the same section, we see that the onset of the amplitude reduction coincides really well with the onset of pre-slip in these experiments, so about 35-62 seconds approximately. And this relationship barely changes even when we partition out the role of the stress increase in the wall rock, which is the blue curve. So in the blue curve, I've removed the effect of this stress increase using the nonlinear parameter that I showed you in the previous slide. Okay, and the yellow star simply shows the location of a reference waveform that I pick for all of these analyses for each event. Now, when we look at the velocity response, this is what is really cool to me. So remember that this composite velocity in black that I told you about has a very short-term anomaly, very close to failure. And the composite velocity represents the effect of velocity throughout the entire 3-block 2-fault configuration. The interesting thing is that when we partition out the role of the stress increase in the wall rock, which is this blue curve, the velocities look very similar to the amplitudes now. And if you're not convinced by this qualitatively, I have another test I'll show you in a second. But what this tells us is that the short-term velocity changes must be due to some sort of a competition between an increasing velocity due to increasing stresses in the wall rock and a decreasing velocity due to pre-slip on the fault. So these two forces or effects sort of outpace each other, and during the early part the increase in the stress in the wall rock wins, and during the later part the pre-slip modulated velocity signal is dominated here, which is what shows up as this delta t velocity precursor. Okay, so maybe at this point you're thinking, hey, this is really cool for this one event, but does this work for my entire set of hundreds of stick slips? So
can I ask you a question here?
Yeah, for sure.
When you mention the wall rock stress variation, do you refer to shear stress variation, not to normal? Because normal is imposed, no?
Yeah, exactly. So the normal we keep as the background in both of these cases. That's just a constant normal load. So the shear stress variation comes from, in this case, the shear stress variation is a consequence of the background, the constant imposed strain rate. Here, we don't have any such thing. So we force a shear stress variation or a vertical load variation.
And the second question is, when you have the shortening of the thickness of the layer, do you know in these experiments how thick is the fault zone? So which is the thickness, if you have a measure of this with respect to the sample?
Right, so the fault zone thickness in this, at least initially when we prepare it, the thickness is about 200 microns. And then once we compress it, it becomes less to about 100 microns. And I have checked whether the dilation of the fault itself can explain these signatures, and it's not enough. So actually, I do have a slide somewhere. Let's see. Okay, yeah. So this is a sort of a backup slide that I had, which shows the dilation and compaction during the interseismic period and during the co-seismic. And what we're seeing in these experiments is approximately for each event a little less than 1 micron of compaction / dilation per stick slip event. And that tiny amount is not enough to explain the entire sort of 2 or 3% pre-seismic variation that we see in these amplitudes and velocities.
Srisharan, another question?
Yeah.
Did you do this with, you're using westerly granite for the sidewalks. Did you do this with steel to check a standard to make sure there's no artifact?
Yes, we did. The problem is once you start using, we did check it with steel and it works, but also with steel, as Marco might be able to tell you, it is really hard to make much sense of these results, because then you're putting gouge in between the teeth, and then the teeth also comes and plays a role in how these amplitudes and velocities are propagating, and it's just really hard to interpret it because these signals are not nearly as clean. So it's kind of hard to say, okay, there's an anomaly here, for example.
Right, just wanted to know that you had verified whether or not all the effect was due to the effect of the wall rock, the westerly. Yeah,
so let's see, I might have a good...
You don't have to show us, but...
no, for sure. We did check to make sure that the role of steel is not accounted for.
Fine. Thanks.
Yeah.
Shreedharan, another question. I was wondering if you tested the effect of the ultrasonic pulse frequency on this difference in between the amplitude and velocity effect, because you are sampling the pore space basically with the wave velocity, right? With the ultrasonic wave. So the frequency should have an amplitude depending on the resolution that you have, right?
Right. And that's a really good point. I myself have not done that. I've just used a frequency so in this case, I use a 500 hertz half sinusoid pulse. And that frequency is equal to the resonant frequency of the sensors that we're using. But I know that Parisa did a little bit of work for a manuscript that just got published, where she looked at that frequency she tried a few frequencies from 100 hertz to 500 hertz. And it seems like overall between 200 to 500 hertz, the response is more or less the same. Although the amplitude of the response might differ, but it has the general shape as these amplitudes and velocity responses. But I'm pretty sure that some of the folks from Reza Hedayat's group in Mines, Colorado School of Mines, have done a lot more work on the frequency dependence of some of these results.
And Sharon, just checking, you're saying hertz, and I think you mean kilohertz.
Sorry, yes, kilohertz. Good point.
Yep.
Srisharan, I have just a curiosity.
Yeah.
But does this result change with the experiments? So in a way, the more experiments you do, the more cracks you may introduce in the blocks, and that could affect the results?
I think it does. The problem is that it's completely anecdotal because I haven't looked at it in much detail, but I know that experiments that I did early on versus later on, the more cracks that it does develop, I think very close to the fault, it develops some permanent deformation, and that does affect the signature more and more. But the issue is that these blocks don't last for very long, and I end up breaking them accidentally after, like, say, 10 or 15 experiments. So that's my entire sample space. But that's a very good point. I should go back and look at it more systematically.
Oh, that's very interesting results, actually.
Yeah. I can say that these results are much more profound and prominent when I use larger side blocks. So these that I'm reporting, that I'm showing you here, are for 5x5 side blocks or contact area. But when I use 10 centimeter by 10 centimeter blocks, so bigger blocks, the difference between the amplitude and velocity is much more significant and very obvious to see. Okay. If there are no more questions, I'm just going to go to the next slide.
Just because the bigger blocks are more compliant?
I think that, yes, I think, well, right. And I think a second reason might be that the bigger blocks, I think it has less to do with the fact that it's 10 by 10 and more to do with, let's see, I'm going to go back to this figure here. So actually this one. So this width of the block itself is much wider for the 10 by 10, which means that more of the wall rock deformation can be accommodated. So in the 5x5 blocks, the wall rock width is about 1 centimeter. In the 10 by 10 blocks, the wall rock width is more like 5 centimeters.
Makes sense. Thank you.
Yeah. So it might be more that than the area itself, I should specify. Okay. So yeah, if maybe at this point, if you're not convinced that this is real and it might be a one-off thing, I may do a sort of simple, quick verification here, where I plot the delta TA, which is the temporal onset of the amplitude precursor on the x-axis, and the delta TV, which is the temporal onset of the velocity precursor on the y-axis. So they should fall on the 1-to-1 line, if they onset at the same time. So for the black curves, which is the uncorrected velocities, you can see it falls below the 1-to-1 line, which says that the amplitude precursor onsets earlier. But when I do this sort of dynamic acoustoelastic correction, the dots are all shifted up and they follow the 1-to-1 line much more closely, barring some, some spread, some noise, which we thought that this was a really cool sort of confirmation that we're on the right track in this case. Okay. So yeah, I'm starting to put this together, thinking about this as sort of a model of precursory slip, and showing you some examples from nature that sort of corroborate or validate our model. So the cartoon on this left here is a cross-section of the fault core, and the circles for me are sort of a theoretical distribution of contacts that make up our fault interface. So in this model, during the interseismic period, we'll start with the interseismic. The fault zone is healing and the contact area is increasing initially. Simultaneously, the cracks in a damage zone, like what Marco just mentioned, also close due to stiffening and increase in the stress, sort of the tectonic loading or strain accumulation, which I'm showing as thinner dashes are the closed cracks and the thicker dashes are the open cracks closer to the fault core. So as an example, so this kind of model is more or less what was kind of invoked, I should say, based on the changes in the seismic velocity after the 2004 magnitude 6 Park Field earthquakes. Post-seismically, you see a recovery or increase in velocity consistent with sort of increased fault locking or healing. During the pre-seismic stage, which is what we're sort of more interested in, the fault is starting to slip. So the contact area is reducing. There are fewer circles here. And this is the sort of the onset of pre-slip, and in nature may be marked by foreshocks or a reduction in the fault zone elastic wave amplitude or velocity in the lab. During this period, the overall stress around the fault continues to increase. And that's sort of the big point, is that the tectonic forcing is still happening while it starts to sort of pre-slip in our lab. And because the far field ultrasonic velocities are sensitive to both the crack density and the slip rate, the velocity anomaly occurs much closer to failure in my experiments. And again, this was, I guess in many ways, we were very fortunate because this paper came out by Claudio very close to when we were trying to publish these results. And it really, I think, confirmed our story at the lab scale, where they showed they looked at the Amatrici, the Norcia-Viso sequence in Italy, and they noticed based on a crustal tomography that the far field velocities, which are in blue here, showed no precursory anomaly. But the velocities which were very at a location very close to the hypocenter in red showed a velocity anomaly that was about, a precursory reduction of about 25 days before the main shock. So this is really cool because this validates our centimeter scale hypothesis on sort of this massive crustal scale. And even though our hypothesis does not involve any pore pressure or anything like that, this is very similar results over two very, very different scales, where we show that the far field velocity precursor may potentially be masked by something that's happening tectonically due to tectonic stiffening. And that's sort of what I'm trying to show you here on very similar results. So in our case, the blue corresponds to a variation in the fault zone and bald rock VP, which is sort of this cumulative VP variation, which has a tiny precursor, which is presumably not resolvable in nature. Whereas when we look at just the fault zone VP, we see a much bigger precursor, which is what they've been able to see in their natural system as well. And a very similar mechanism, identical mechanism, I should say, was invoked in this case. And this is sort of one of the reasons why precursory signals may not be more common in nature, because the anomalies that are linked to nucleation and pre-slip are very easily or can easily be masked by tectonic stiffening in the wall rock. Okay, and finally, co-seismically, during the actual earthquake, you have a lot of stuff happening. Many more asperities are destroyed as the fault slips very rapidly. So there are fewer asperities in contact. And if you have a complete stress drop, maybe there are no asperities in contact. The entire fault and damage zone experiences a sort of reduction in the deviatoric stress, and you have cracks in the damage zone that reopen and new fractures may be formed. So almost everything is open. It's a lot of cracks. And of course, this co-seismic velocity reduction has been observed in numerous cases. I'm showing you the same example as the interseismic case, but this is something that has been documented all over the place. And this co-seismic velocity reduction in nature is often attributed to a potential increase in the crack density during an earthquake, and it's partly the same mechanism that we're invoking. So now we're convinced that the lab precursors are robust, and we also know where they originate. And so the next question, hopefully I won't spend too much time on this, is what to do with them. So this is sort of where I talk a little bit about some of the prediction type exercises that I've been doing, modeled after some of the cool results by Bertrand, Claudia, and others at Los Alamos. So Chaz and I started working on this early last March-ish, where we just sort of started playing with our data to see if we can use similar machine learning prediction exercises on the amplitude and velocity signatures. So similar studies have been used in labs to, in lab type studies for earthquake prediction. For example, here, this is by Claudia, where they use acoustic emissions released during the lab events. And in this one by Jess McBeck, they integrated the strain field derived from X-ray tomography during a triax experiment on intact rock to look at how it fractures. And last panel here, Fabio Corby did this really cool GPS exercise on a synthetic gelatin fault, which was used for event prediction. So in all of these cases, the machine learning works really well, but in some ways, maybe it's not very clear why or how sort of the internal mechanics of it makes it work. But the cool thing is that because we're using the ultrasonic properties that are directly tied to the physics of grain sliding, properties that are directly tied to the contact stiffness or the real area of contact, we can potentially provide a physical underpinning for how these things work if we performed a machine learning exercise on our results. So I'm just going to quickly talk about whether the lab earthquakes in my experiments are complex enough to even warrant prediction. So on the left, I'm sort of defining a few terminologies for a couple of events. So for any given co-seismic, you can estimate a time to the next event and a time since the previous event. And this can be used to see how periodic the lab events are, because if they're perfectly periodic, the time since the last event and time to the next event should fall on a 1-to-1 curve. So these dots represent some of my experimental lab quakes. And you can see that there's a much bigger spread than just this sort of perfectly falling on the 1-to-1 line. And the spread is somewhat more as the stress drop starts to increase. And so this shows that our experiments are relatively complex and bound by period doubling, which is the 1-to-2 and the 2-to-1 lines. And machine learning would potentially be a useful exercise because we can't just get away with simple constant reoccurrence interval models. And sort of before diving into the results, I want to define a baseline or a benchmark that I'm hoping the machine learning exercise can beat. So now in this case, I assume a constant reoccurrence interval model, which is the screen model here. It doesn't know anything about the mechanics of this experiment at all. I just assume a constant reoccurrence interval that I get from the entire experiment. And the y-axis is the time to failure, x-axis is the experiment time. So the black is the experiment data, which is Visually, you can see the green curves do a very poor job of matching the black data, except for maybe this case here, and in some ways this case here. And that sort of shows that the constant reoccurrence model is somewhat inadequate to describe our lab earthquakes. I use a similar, for the machine learning exercise, we used a very similar implementation to what Claudia did in that Nature Geoscience paper that I showed you earlier, where we use sort of gradient boosting, which is a form of supervised machine learning. And this is a relatively simple regression algorithm and works by iteratively minimizing misfits. So if you have a set of samples, which may be these dots here, bound by the green corresponding green ground truth, the first tree in gradient boosted trees represents a poor fit to the ground truth, and each subsequent tree minimizes the misfit between the samples and the previous tree. So the error is reduced as you increase the number of iterations. And you can visualize this through this animation on this figure here. Hopefully it's moving for you guys as well. The data or samples that you have that you're feeding into the model are known as features, and the functions that you want to predict are the labels. So it's just you can reduce it into a simple XY problem, which is what I try to do in the next couple of slides. So here I'm just talking about setting up this earthquake prediction. Now the labels or the unknowns that we want to predict, I have 3 of them, which are time to failure, time since failure, and the shear stress of throughout the experiment. All of which, so the time since and time to failure are estimated from the shear stress. So they're all derived from the shear stress, which is just measured from a load cell during the experiment. Now, the features I'm using are just the amplitudes and velocities. In this case, I don't have to resort to using statistical features of any sort because I specifically already know that the amplitudes and velocities are in some ways tied to the physics of the problem because we already explained that in a lot of the previous slides. So we have prior knowledge that the amplitudes and velocities are related to the shear stress in some complex fashion. First, I sort of smooth the features and remove any long-term trends by normalizing them so that I don't want the long-term amplitude or velocity trends that may come from layer thinning, dilation, etc. And when I say dilation, layer thinning, I mean long-term experiment scale. I still want the information that happens during each event. So there is still a problem though, even after doing this exercise. Now, if you look at the data, there is a non-unique relationship between the features and the labels. So what I mean by that is that for a given amplitude or velocity, let's take this value here, something just above 2%. You can have 2 different values of the shear stress label. So at the exact same value of amplitude, depending on whether it's on the increasing or decreasing limb of the feature, you can either have a smaller shear stress or a larger shear stress. And that's no good because you want a one-to-one function here. So I fixed this by slightly offsetting or clock advancing the feature, which is the blue one here. So I've just shifted the same feature by X data points or X time points. And in our machine learning algorithm, I use both the original and the clock advanced feature for the regression. So this provides it the additional information about the gradient and tells the algorithm whether we're on the increasing or decreasing limb of this problem. And so that ensures that the problem now is unique or has a unique solution. So just to summarize, we can think of this as a simple sort of functional y equals f of x problem, where the y's are the unknowns, the shear stress, the time since the last event, and the time to the next event. And the f of x feeds in the ultrasonic properties, which we already know are proxies for the real area of contact, stiffness, and the wall rock stress state, because we've already discovered that in the previous slides. Okay, so sort of the big punchy thing is that this works, and it works really well. When we go through this prediction exercise, we see some really cool things, and we just heard back from the reviewers on this work, and I'm working on the revisions now, is that the crux is that it's a very simple machine learning model which performs exceedingly well in predicting all 3 parameters. The black lines are the experimental data. The blue jittery curves are the machine learning models. And this gray curve at the bottom is the mean squared error for each of these sections. So the cool thing is that the overall prediction is really good, but also it seems like it's better as you approach failure for the shear stress and the time to failure. So as you get closer and closer to failure, the model is able to better predict the failure. And for the time since the last event, it seems like the model performs really well at the beginning and becomes poorer as you go further away from the start. So we're not entirely sure, I'll admit, why exactly this works this way, but one hypothesis is that if we relate this back to what we think the amplitudes or what we know the amplitudes and velocities represent, it sort of indicates that the post-seismic increase or the healing portion of the amplitude and velocities potentially contain some information about the previous event, which is why it's better here. And the sort of later precursory phase of these features, the amplitude and velocities, contain some information about the impending seismicity or the next event, which potentially comes from the pre-slip. And that is possibly why the predictions are better closer to failure for the shear stress and the time to failure. So I think there's a lot to think about and to be done here in terms of what this means for, crustal scale faults and seismicity, et cetera. And just recently, I think last week, Parisa published this really cool work on using some more sophisticated models, which further improve the accuracy of the predictions. So going sort of away from XG boost or gradient boosting and using some time-based models. So LSTM, for example, which incorporates the temporal variation in our features into the prediction exercise, which significantly improves the model performance. And you can read more about that here. Okay, so just to sort of conclude, the sort of main points are that the elastic wave amplitudes are very robust indicators of pre-slip, and velocities are modulated by pre-slip and tectonic stiffening. So they are potentially manifest as weaker signals, but signals that contain information about the stress state of the fault as well. And finally, these precursory variations, at least in the lab, because they're tied to the evolution of the real area of contact and contact stiffness, can be coupled with machine learning models to accurately forecast the earthquake imminence. And so I'll just leave this summary up and take any questions or any more questions that you may have. Thank you.
I'll invite all of you to unmute long enough to very nice and clear. Yeah, and please just use the raise hand feature, and we'll go ahead and start off with a question and discussion period. And we want to encourage everyone, and maybe especially people early career, but anybody who'd like to start. Massimo Coco, please go ahead.
There is Elisa before me.
Massimo, excuse me. Yeah, I was not paying attention. I didn't realize that Elisa and Chris
Don't worry.
Johnson was already there. Elisa, please.
Okay. Thanks so much, Srisharan. Very clear talk. And I have 2 questions. One is if with the machine learning you use both of the features together, or if you try to infer the information by using only amplitude or p-velocity separately, you obtain different results. First question. And second question is about time to failure. You compute the time to failure from the peak of stress or from the drop of the stress? So for the minimum stress level or from the maximum?
Yeah, so I think the second one is a little bit easier, so I'll get at that first. The time to failure, I define failure as the peak stress.
Okay.
So the co-seismic itself, if you see here, I keep it as 0 because I see that as failure is still happening. So I don't see the need to increase or change time since or time to failure. So they're both at 0 during the co-seismic. At the minimum, they both start changing again. So it's only from minimum to maximum. That is the period during which both of these features change.
Yes, but the next event for you is the maximum stress level.
Right. The next event is the maximum stress level. The previous event is the minimum stress level.
Okay. And did you find any difference between slow events, fast events, locked seismic cycle or creeping seismic cycle?
When you say difference, do you mean like in terms of performance?
Yes.
Not particularly. I think they all work really well. I don't know if I maybe have actually I don't have one. Let me see.
No, don't worry. Only if you remember.
But, yeah, they all worked really well. There wasn't any specific hiccups. And I forget your previous question. Sorry.
If you use separately the two features or together.
Right. So, yeah, I did all of them.
Okay.
I tried train and test on using just amplitude, just velocity, a combination of both. And it's interesting, really. Just amplitude works the best. Just velocity also works very close to it. Using both amplitude and velocity reduces the performance. And I do have an explanation for that. I think that's because they are giving it different potentially conflicting pieces of information. So if you look at this, right? Amplitude says that it's starting to decrease early in the seismic cycle. Velocity says that it's starting to decrease later in the seismic cycle. So I think the issue with giving them the raw amplitude and raw velocity is that they're both telling the algorithm to do different things. They're feeding it different pieces of information. So it sort of tends to, in some ways, mathematically potentially cancel out, for lack of a better word. And so I found that reduces the performance much more. But my guess is that using a more sophisticated algorithm that can account for this will fix that issue. For example, in Parisa's manuscript, if you see, it seems like that is not an issue when she uses something like LSTM, for example. So that might be an algorithm issue.
Okay, thanks.
Yeah, thank you.
Massimo.
Massimo?
Yeah, I was waiting authorization by Chris. Okay, so thank you very much. It has been a wonderful presentation and very exciting. I would like to try to better understand which is the proxy for a fault model that you have in your case. Because you are using with westerly granite. You have bare surface at the beginning. Mm-hmm. Because one of the key outcomes is that the wall rock stress state does matter. Mm-hmm. So this means that you have a gradient of a sort of localization process in a broad region. Now, exactly. The question is this damage region determined just by the occurrence of seismic event and seismicity or micro events, and therefore you have a broader region affected by these stress variations? But if this is the case, why the wall? So how do you find the wall rock stress state? So is the wall rock just external to the sample, or the wall rock is surrounding the principal slipping zone?
Right. That's a really good point. In this case, I think I say wall rock as a sort of, a discrete quantity, which it is really not. Like you say, it is a gradient, because I imagine, like, let's say in this example, if I consider this to be my wall rock, this to be my westerly granite, my guess is that somewhere close to the edge where I'm applying the normal stress, the changes in velocity in the granite are much less. And most of the changes are accommodated very close to the fault. So it's really hard to tell, because the way we've done this is we've taken all the the velocity variations are less here and more here, and we've sort of averaged it over the entire sample and assigned it to one point on the granite. So yeah, I'm not really sure I have a good answer for you there. Yeah.
Because therefore means that if we consider that your wall rock stress state is just the stress state applied to the entire sample, therefore what is determining the rate of acoustic emissions, of the rate of earthquake production, is determined, of course, by the redistribution of stress and the localization process that you have at the micro scale during the loading history across the seismic cycle. But this to me is important, because if